9.5 Antiderivatives and indefinite integrals. Well, antiderivatives, what does that mean? The prefix anti means, in English, means opposite, against. So, for example, someone who is social is someone who likes to talk, hang out with other people. That's social. Antisocial, well, is someone who does not like to talk, hang out with friends, etc. So if you're antisocial, you're quiet, you don't want to talk, you don't want to do social things. Clockwise is the direction of our clock from 12 to 1 to 2 and so forth. So if we start on top and we make a circle, clockwise means we go right and then down and then left and then up. Anticlockwise is the opposite. We go the other way. So we go left first and then down and then right and then up. Derivative. Well, the derivative, for example, of 3x is x, right? So the antiderivative is the opposite. The derivative of 3x is 3, not x. So the antiderivative of the 3 with respect to x is 3x. Well, that's one answer anyway. So antiderivative is just the opposite of the derivative. So here's some examples. If g of x is equal to x to the fourth power, then the derivative g prime of x must be equal to 4x to the third power. The antiderivative is the opposite of derivative. We can write it as capital F of x, or big F of x. Because it's the opposite, in fact, the derivative of big F of x is actually equal to f of x. We'll see this later. So example, if f of x is equal to 4x cubed, then the antiderivative of f of x is equal to x to the fourth power. So big F of x is equal to x to the fourth power. Why? Because if big F of x is equal to the fourth power, x to the fourth power, then the derivative of big F of x must be equal to 4x cubed, which is what we started with. Some more examples of derivatives and antiderivatives. The derivative of x to the sixth power is 6x to the fifth. Notice that the 6 comes out in front, so we multiply by the number in our exponent, and then our power goes down by 1. 6 becomes 5. Well, the antiderivative is the opposite. So if f of x is x to the fifth power, then the antiderivative big F of x, instead of multiplying by the exponent, we divide by the exponent. So it's 1/5 x. And instead of going down by 1 power, we go up 1 power. Now some people might think that's right. Let's check to see if that's right. The derivative of 1/5 x to the sixth power is not x to the fifth. Something is wrong. What is it? Well, it shouldn't be 1/5. It should be 1/6. So the idea of dividing instead of multiplying is a good idea, but we have to divide by 1/6 when it's x to the fifth. So to generalize, if our g of x is equal to x to the n power, then the derivative is n times x to the n minus 1 power. And for antiderivatives, if f of x is x to the n power, the antiderivative big F of x is going to be 1 over n minus 1. 1 over n plus 1 times x to the n plus 1 power. Okay. That's why x to the fifth becomes 1 over 6 times x to the sixth power. The derivative of sine x is cosine x. So the antiderivative of cosine x is sine x. The derivative of cosine x is negative sine x. So the antiderivative of sine x is actually negative cosine x. Okay. Next, The derivative of ln of x is 1 over x. So the antiderivative of 1 over x must be ln of x. Okay. So what have we learned so far in this course? Derivatives tell us that if we know our value, which is also the accumulation, let's call that big F of x, then the rate of change would be the derivative of big F of x, big F prime of x. From integrals, we know that if we know the rate of change, small f of x, the accumulation, which is big F of x, is just the integral of small f of x, or the integral of small f of t, small f of t dt from a to x. In both cases, well, for derivatives, we say that the rate of change is the derivative of our value, big F prime of x. For integrals, we say that the rate of change is just small f of x. Therefore, small f of x is actually equal to big F prime of x, where big F prime of x is the derivative of big F of x, which is the derivative of the integral of x. This is the first part 1 of what's called the fundamental theorem of calculus. Really, the big idea here is that the derivative of the integral of f of x is equal to f of x. We get back itself. Derivatives and integrals are opposite. They're inverse operations, like addition and subtraction. What do I mean? Well, any number plus 4800 minus 4800 gives us a. If we take f of x, if we take the integral of f of x, and then we take the derivative of that, we get back f of x. We get the same thing because they're inverses. So with any number, if we add it and then we subtract by the same number, we get back the original thing. And with any function, if we take the integral and then we take the derivative, we get back our original function. Okay. Next, so we have antiderivatives. We also have indefinite integrals. Let's look at some functions. F of x is equal to x squared. What's the derivative? Well, it's 2x. Next one, g of x is equal to x squared plus 1. What's the derivative? Still 2x, because the derivative of 1 is 0. H of x is x squared plus 17. The derivative is 2 of x. Y of x is x squared plus 725. The derivative is still 2x. So for any function x squared plus c, where c is any constant, any number, the derivative is always 2x. Okay. Now, if f of x is equal to x squared, we say that the antiderivative of big F of x is, if f of x, let's say if g of x, let's say if a of x is 2x, the antiderivative of big A of x is going to be x squared, right? Because x squared gives us, if we take the derivative of x squared, we get 2x. So antiderivative of 2x is x squared. But really, we can also say the antiderivative of a of x is equal to x squared plus 1. It's also okay. They're both antiderivatives of 2x. Now, in the last lesson, we wrote areas under the curve in terms of integrals. And we know that we can approximate that with Riemann sums. Well, if we don't care about our boundaries, we have this thing called the indefinite integral, just the integral of fx dx. Well, if we have f of x is equal to 2x, then the indefinite integral is just like the antiderivative is going to be x squared. but we also have to do plus c because this is the general form. So some examples. If little f of x is 4x cubed, then we can say the antiderivative is x to the fourth power, plus any number is fine. So the indefinite integral of fx dx is going to be x to the fourth plus c. If our function little f of x is x to the fifth power, then the antiderivative would be 1 over 6 x to the sixth power. Our integral would be 1 over 6 times x to the sixth power plus c. One more, if our little f of x is 18x to the sixth power, then our antiderivative, big F of x, well, we know it's going to be the seventh power, and we have to do 18 divided by 7, because we have to divide by our exponent. Okay. Not 18 divided by 6, it's by 7, by the exponent that we end up with. So if f of x is 18x to the sixth power, the indefinite integral of f of x dx would be equal to 18 over 7 x to the seventh power plus c. Okay. To understand what we talked about, let's put it in context. Let's say that Danielson starts working today. He makes $15 per hour. Well, the rate of change, let's say the rate of change is small f of t. Well, it's going to be 15 because that's how much money he makes per hour. Then the antiderivative big F of t would be 15t. Why? Because the derivative of 15t would be 15. In other words, the rate of change is the same as the derivative of the antiderivative is 15. How much money will Danielson have after 2 hours? He starts with nothing. So after 2 hours, he will have 15 times 2, which is $30. That is also equal to the antiderivative of f at t equals 2. Meanwhile, big F of 5 will be the money that Danielson will have after 5 hours. That will be 15 times 5 equals 75. And we said that's true because the antiderivative is always 15x, so we just plug in what x is. Meanwhile, the indefinite integral, what would that look like? That would be the integral of f of t dt, which is equal to the integral of 15 dt. That's it. Okay? That's it for this lesson.